Thin lenses. A lens is a transparent object with two refracting surfaces whose central axes coincide. The common central axis is the central axis of the lens. A lens that causes light ray initially parallel to the central axis to converge is called a converging lens. If instead it causes such ray to diverge, the lens is a diverging lens. When an object is placed in front of a lens of either type, reflection by the length of light rays from the object can produce an image of the object. Converging lens, we look at this part. We enlarge it, the light parallel to the axis and can converge. Diverging lenses, you look at this part, okay. The light parallel to the central axis is diverged. A thin lens has two focal points symmetrically placed on either side of the lens. We must be careful to distinguish between them. Look at this one. This focus on this side, and this lens first focus this one. Okay? Yeah. This is F2, this is F2. Well, look at the C, the arcade. Okay. Real image formed on the side of the lens that is opposite object, and virtual image formed on the same side as the object. This is a lens is different from mirror. In the case of mirror, behind the mirror is virtual size, but in the lens after the mirror lens is a real size. Okay, so this is real size, and the same size as the object is called a virtual size. A lens can produce an image of an object only because it can bend light rays. But it can bend light rays only if its index of reflection differs from that of surrounding media.
This is a pair of hollow lenses with thin plastic faces and air in between, as shown in this diagram. If we place this hollow concave lens in a beam of light, the light is only slightly affected. If we insert the lens into a beam which is passing through this tank of water, the air-filled concave lens now brings the beam to a focus at a point close to the lens. What will happen if we allow the lens to fill with water? When the lens is filled with water, it no longer focuses the beam of light. What will happen if we insert the water-filled lens back into the beam of light in air? The lens now spreads the beam. Here is the same sequence repeated with a hollow convex lens.
We should consider only the special case of a thin lens, that is, a lens in which the thickness part is thin compared to the object distance p, the image distance I, and the radii of the curvature R1 and R2 of the two surfaces of the lens. We should also consider only light rays that makes a small angle with the central axis. They are exaggerated in the figures here. They have two formulas, 1 over p plus 1 over I equal to 1 over f. It looks like exactly the same as the case for Miller, but actually it's not, because f, 1 over f, calculated a different way. These two equations we call the length makes equation. Okay, R1 is the radius of the curvature of the lens surface on which the light falls first, the first one. Okay, light falls first. R2, the radius of the curvature of the second surface of the lens. N is index refraction. It is defined by n length over n median. Usually the median is air, so n median is 1. Okay. The thin length of formula, we deduce, prove it. Okay. Now, suppose this is thin length, we exaggerate this error. This error should be much smaller compared to the P, R, R2, I, okay, which is exaggerated. Okay. It has two refracting surface here. Okay. Look at the first one. This object, the line from object hit the surface in the face. And so this perpendicular normal force, so it refracts from here. And this line intersect with this line. This line, they never change direction, so the center. So this is the image, and we call it, this is I prime, from this to here. In this case, is negative number because it is in the same size as object. Since this is a reflecting surface, we use this formula. In this case, N1 is 1 air. N2 is index refraction. Okay, R is this R, and this R, you see that's one. The center is in the rear part. In the rear part for this refraction surface. So R is positive number. Okay, and this I prime is negative number. Okay, now we rewrite it. We write I prime is positive number minus. That means this is a positive. Okay, altogether should be minus, all right? Yeah, it's just a different way to write it, okay? Yeah. This is N2 is N, N1 is 1, this is R1, okay? Now, this line continue, and then we have this one, okay? We get this equation. Yeah. This lines continue, hit the second reflecting surface. This is normal, so it reflects to this point. And this central line never changes, so intersect in the position where the object, the image, okay? So in this case, this is I double prime, okay? And for this pages, this is P double prime, okay? This is R, okay? And this is air. We know that we exaggerated it. Now we calculate this one, okay? For this one, I prime, P prime is what is equal to this one. This one, I prime. This one, remember, this is a positive number, okay? So we don't write I, we say I prime. This positive number we define. This is a positive number, okay? And then in the left, air. Since air is much smaller to the eye, so this one becomes I prime. And we use the formula for this refracting surface. And this one, you see, this is P. Each side, this is the N. This P is equal to I prime. And on this is air. So this N is 1, this is R prime. This I prime, okay? This is the image of the lens, okay? And this is a 1, this is a 1, this is N, so 1 and N, this is R prime, this is R prime, okay? Yeah, and this I prime is positive number because, I'm sorry, it is negative number, okay? Whatever. This I prime is I. Final image position. Okay, so we put them together, okay, and then we find out that this is equal to I, okay, this is I prime, and this one cancel out, and when the positive and minus. So 1 over P plus 1 over I equal to this, equal to n minus 1, this is R prime minus R2. This is the formula we have proved. Okay. In this case, R1 is R prime, R2 double prime. Locating image of extended object by drawing rays. We can also locate an image by drawing rays. We have 3 rays to draw. First one, ray 1, is parallel to the central axis. After the reflection, it passes over the focus F2. Second ray, reverse, is starting from the passing the focus, and after you hit this one, reflect is parallel to the axis. And retreat, they pass the center of the lens. It never changes, it goes straight. And intersect of these 3 lines is the object, the image position. Okay. Now let's see different situation. Okay, this is object you put inside the focus line, and we find out now this is the object with parallel. It goes to the focus. If you go to focus, which one? Which one is this one? Okay, this is the focus. Okay, object go focus. You get a parallel, okay. And then if you go to the center of the lens, it never changes. These 3 lines intersect at this point. This is the position of the image. We looked converging lens. Okay, the first one parallel to the axis, and it go to not this one, this one. Okay, it diverges. Okay. Now, second, it goes to this focus line, this line. After the reflection, it parallel to the axis. The third line is pass through the center of the lens. It never changes. These 3 lines intersect at this point. This is the position of the image. A ray that is initially parallel to the central axis of the lens will pass through focal point F. A ray that initially passes through focus point F, initially for this one, will emerge from the lens parallel to the central axis. A ray that is initially directed towards the center of the lens will emerge from the lens with no change in its direction. Because the ray encounters the 2 surfaces of the lens where they are almost parallel. The image of the point is located where the rays intersect, on the far side of the lens. The image of the object is found by locating the image of the 2 or more of these points. Converging lens. We look at the R2. R2 is the radius of the second surface. The center is here. Okay, center there. So this is the virtual side, so the R2 is negative number. P is always positive in any case. Okay, so we find the real image, inverted image. Now, this is we draw. If we put the object inside the focus point, this R2 is also here. Okay, in the virtual side is smaller than 0, but this P is smaller than F, and we get this virtual upright image. Diverging lens. We look at this. In any case, the R1, this R1 is on the virtual side, is negative number, okay? And R2 is positive number. So in any cases, we get virtual upright image. Diverging lens never get real image. Now let's summarize it. We look at the lens type, the object location, the image, real or virtual, location, orientation, and a sign F, T, I, and M. We rewrite this one as I equal to PF over L. Okay? And we know M is defined by minus I over P. And we get I over P minus this M. M larger than 0 is upright. M smaller than 0 is reverted image. Okay? Now, let's see the converging lens. Converging lens means F is larger than 0. P is at 0. So in this case, FPO positive. So PF is positive number. And whether I is positive or negative depends the magnitude of P and F. The first case, P is smaller than F for the inside the focus. So this is smaller, this is negative number. This is a positive number, so I is negative number. Now, we put the object here. P is smaller than F. Then we find the I is smaller than 0. I is smaller than 0, put here. M is larger than 0. M is positive. What this means? This means we have an image in the virtual side. Okay? And M larger than 0 is upright. So we write this. Converging lens, they put location objects inside the focus point. We get virtual image, location in the same size of the object, and orientation is the same, upright. And then we found F is positive because converging lens. I is negative because virtual image. M is positive by this definition. So it's upright. Then we put the objects outside F. This is positive, positive. You put the outside F, that means P is larger than F. So this is positive. Okay. Then both positive, I is positive. I is positive, M is negative. So I is positive means the real image. M is negative, then the inverted image. Okay. So we put on here, we get outside, we get a real image. Its opposite is the opposite, the lens. Can be real. And it's upside down, reversed, inversed. The F is positive because converging. I is positive because calculation. This FP is larger than F, and M is positive. Okay. The sign of I and M is always opposite because P is always positive. Next, diverging lens. Diverging lens F is smaller than 0. So this negative smaller than 0 is positive. P is positive. F is negative. So I is always negative. Never get a positive. Okay? Okay. So we always get the virtual image on the object side. Okay? So I is negative, M is positive for this one here. So we get this one. This diverging is location can be anywhere, or the object put anywhere. We always get a virtual image, and is the same size as the object, and it's upside right, and the same orientation. In this case, I is negative, M is positive, and this F, because diverging, F is negative.
We'll use this light box and a set of large acrylic lenses to show how light beams are focused by various lenses. Here is a convex lens with a relatively long focal length. This convex lens has a shorter focal length. This concave lens has the same focal length as a second convex lens, but spreads the beams instead of focusing them. If we place these two lenses together, their effects cancel and the beams pass through unchanged.
Magnifying glasses are commonly used for enlarging print. We'll use these two large magnifying lenses and a backlit grid to demonstrate enlargement by a single lens. When this large plano-convex lens is held against the grid, the image seen through the lens is only slightly magnified. If we move it out farther from the grid, the magnification increases. This plano-convex lens has a shorter focal length than the last lens because its surface curves more sharply. If we place both lenses at the same distance from the grid, the lens with a shorter focal length gives a greater magnification. Here is a plano-concave lens with one surface that curves inward. This lens magnifies by a factor less than 1, producing an image which is smaller than the object. This animation shows how the light from one square of the grid is bent inward by the convex lens, making the square appear larger to the camera because it appears as if the light is coming from these positions. If we move the lens farther out, the square appears even larger. A convex lens can project a real image of an object on a screen. We'll use this setup to look at the images produced with different lenses. This lens has a relatively long focal length and will focus a real image on the screen only at a long distance from the object. It will also focus a sharp image when it is approximately that distance from the screen. This lens has a shorter focal length and can focus closer to the object. If we move it to approximately that same distance from the screen, it produces another sharp image. Here is a device known as a Fresnel lens. The lens magnifies objects seen behind it much like an ordinary lens, even though it is only a millimeter thick. A series of concentric grooves in the lens provide the magnifying power. Each groove is cut to an angle, which depends on the radius of the groove, as this enlarged drawing of a side view shows. Each of the concentric grooves is cut to the same angle that the surface of a normal plano-concave lens would have at the same radius. The Fresnel lens provides the same magnifying power as an ordinary glass lens, but with much less weight.
Two lens systems. When an object O is placed in front of a system of two lenses whose central axes coincide, we can locate the final image of the system, that is, the image produced by the lens farther from the object, by walking in steps. Let lens 1, the nearer lens, and the lens 2, the farther lens. Step 1. We let P1, this is a P1, represent the distance of the object from the lens 1. We then find the distance I1 of the image produced by lens 1, either by use of the equation or by drawing rays. Step 2. Now, Ignoring the presence of the lens 1, we treat the image found in step 1 as the object for lens 2. This one is the object for lens 2. Okay. We take P2, P2's distances, equal to D minus I1, where D is the separation between the two lenses. This is P2 is D minus I. If this new object is located beyond the lens 2, the object distance P2 is still D minus I, but I is much larger than D, so P2 is a negative number. We still use the D minus I, but this number is minus number because it's not here, it's here. That's the only case P is minus I. A similar step-by-step solution can be used for any numbers of lenses, or if a mirror is substituted for lens 2. The overall lateral magnification, capital M, produced by a system of two lenses is the product of the lateral magnifications M1 and M2 produced by the two lenses. Capital M equals M1 multiplied by M2. Sample. A praying mantis prays along the central axis of a thin symmetric lens, 20 centimeters from the lens. The lateral magnification of the mantis provided by the lens is M equal to minus 0.25, and the index of the refraction of the lens material is 1.65. Question A. Determine the types of image produced by the lenses. The types of lenses, whether the object mantis is inside or outside the focal point, on which side of the lenses the image appears, and whether the image is inverted. A lot of questions, okay, only give you 3 data. You gotta judge from these 3 data. We know I equal to minus MP. M is minus 0.03, okay? So we put this M inside, we get I is 0.25 P, because P is always positive, so I is positive. Then we get a conclusion. What is it? I is conclusion, so it's real image. It's real image. The M is negative number, so it's upside down, inverted matches. Okay? Since it's a real image, so the lens must be converging lens. Because concave lens never get real image. Because converging and only it's outside the focal length, you can have a real image. Okay? And because this is real image, is upside down, inverted. Question B. What are the 2 radii of curvature of the lenses? Now we see, we know P, we know I, and we know the formula. So we can find F equal to 4.0, positive number. What is F? This is great. F is 1 over F equal to I n minus 1 over R1 minus 1 over R2. In this case, we know it's converging. Okay, so R2 is negative number. Okay, is negative number because R2 its center is here, is on virtual side. Okay, so we write this one. This is positive R, negative R, negative, negative, positive. So F is positive. Let's put a point. Okay, okay. So we put inside. We get R. Sample. In Figure A shows a halami neo seats O1 that is placed in front of the 2 thin symmetrical co-axis lenses. 1 and 2. With focal lengths f1 positive 24 centimeter, f2 positive 9.0 centimeter, respectively. And with length separation L 10 centimeter. The seeds is 6.0 from the length 1, because the P1 is 6.0. Where does the system of the two lenses produces an image of the seed? Where is the seed? Okay, so we do 2. Okay, first one, we have this one is 6, where the focus F1, so we have I1 easily. I1 is minus H1. What does this mean? This is on the virtual side, is here. So then we see the P2. P2 equal to L minus I1. I1 is minus, so we get P2 is 10 minus minus A is 18 centimeter. Then we have a second one. P2, well, 1 over P2 plus 1 over I2. So we know P2. Okay, we know F2. We can find I1. So get I2, good, 18 centimeter. So it will be this way, direction. It's positive number. It's on this side. So it's upside down image, okay? Two thin lenses of focal length f1 12 centimeter and f2 minus 10 centimeter are separated by d 7 centimeter along their common optical axis. An object is placed on the optical axis 43.5 centimeter from the center of the two lenses. So this actually is 40 centimeter from the first lens. Where is the location of the image? Now, the question didn't tell you which one in the first. This is the one case. Another case is this convex lens in front. So we saw this one. Okay, that's very simple. The first one, f equal to 12. Okay, p is 40. Okay, so we get I1. I1 is 120 over 7. This is much longer than this one, so it's far right. And the P2 for this one is D minus I1. 7 minus 130 is minus 71.7. P2 is minus number. And then we use this formula again. 1 over P2 plus 1 over I2 equal to 1 over F2. We got I2. I2 is minus 710 centimeter. Now, for this one, this is the real side. This is the virtual side. I2 is minus means this way is about far left. Okay, on the left. Now we come to another situation. This is a convex lens in front. So in this case, P1, the same thing, is equal to 40 centimeter. I1, I don't know, F1 is minus 10, so we get I1. I1 is minus A, it must be is in the virtual side, this side, it is here, okay. So then we see the P2. P2 is equal to D minus I1. D 7 minus 15 is this one. This one go this way. And then we have P2, we have F2 is 12, and then we find I2. This one is positive. This is real side, so it's on the right side. Sample. A thin lens is placed on top of a diverging mirror. This is diverging mirror of radius r 10 centimeter. An object S is placed 10 centimeter above the vertex, and the image is overlapped with itself. So this image, or this is objects, they overlap. What is the focal length of the lens? Now let's see how many processes the light went through. First, it goes through the lens, and then it reflects by the mirror. And the light comes back, goes through the lens again. So we get an image. So altogether, we should see 3 processes. Lens, mirror, lens again. Let's analyze one by one. For this lens, okay, we don't know the F, but we know the P is 10 centimeter. We don't know the I. So we can find I1, okay? P2, because this D is 0, P2 equal to D minus I1. So P2 is minus 1. And this is a mirror. Okay, we use the mirror equation. Okay, the mirror equation is, this is F equal to half R, right? F, so this is a 10. Now question is, P2 is minus I, 1 over P2 plus 1 over I2 equal to 1 of F2. The F2 equal to half R. Now question here, you go from here, this R, the center of circle is behind the mirror. So it is a virtual side. So in this case, F is minus number. So we have a minus 10. That's a key point. Okay. So in this case, we have this one. And then we go back. When I go back to when a P3, the distance still D, 0 minus I2. Okay. And we know the S3 is 10. Okay, so you have this one, this is P3, this is I3, this is F. We don't know what's happening. So we have these 3 equations, 3 processes, and we put them together. 1 over I1, 1 over I1 minus, cancel out. 1 over I2, 1 over I2 minus, cancel out. So this is 2 over 10. This is 2 over F minus 2 over 10. So we can find F equal to 5 centimeter. Sample. A solid sphere of radius r and index 1.50, silver over one hemisphere. This is a silver. That means the light reflects here, cannot go through this one, this is it. All incident beam is shining parallel to axis. This light go this way, okay? Which passes through the pole of the unserved, okay, hemisphere. Where is the location of the image? What about the image? Okay, now, okay, this is first hit a refracting surface, and then it will be reflect from the mirror, right? And then it be another refracting surface. So this line and the central line never changes. So this will be the final image. 3 processes, 1 reflecting surface, 1 mirror, 1 reflecting surface again. Okay, this is the most important thing. After you clear this one, we do one step by step. First step, okay, we use this crate. In the crates, N1 1.0, N2 1.5, I2 I want to find P from infinity, okay? R, in this case, this is a reflecting surfaces R here. This is rear part, rear area. This is virtual side, this is rear side. So this R is equal to big R, okay? Then we put this number inside, okay? Put this one inside. P is infinity, again I1. I1 is 3R. Where is it? Now, this is a reference point. reflecting surface center. 3R positive. This is the real side. So 1R, 2R, 3R. It is here. This is S1. And then it be reflected by the mirror. Okay. Now we use the formula. P2 equal to D minus 1. This is 2. What is the D? Now D here is this is reference point to mirror this point. So the D is 2R. This is D is 2R. Minus I1, 3R. So P2 is minus R. What does this mean? This is a reference for the mirror. Minus R here. This is positive. Okay? Yeah. This is a virtual side for the mirror. This is real side. And this F2 is half R, as we know. Okay? Then we find the S2. This is a central line, never changes. A cross-section S2. Now we call this one. P2 equal to D over minus R. This is minus R. I2, we have found this F. What is the F? We call this F equal to half R. F is in real side, so it's a positive number. It's half R. And this is minus R. We find. Okay? And then last we find I2 equal to R over 3. Now, this is the point. Okay? R over 3 is what 1/3 of radius is in real side. For this mirror, this is real side. So this is R2. Then finally, we have to go the reflecting surface again. This time, P3 equal to D minus I2. D is 2R. This one to this one. Minus half range, we get 5R over 3. For this reference, this is 5R over 3. Okay. And in this case, we look from here, and this surface R is in this direction. This direction, if you look from this to this is the real side, this is the virtual side. So in this case, okay, the R is negative number. Okay, N1, N2. N1 is 1.5, N2 is 1.0. This R is minus R. Okay, minus R. So we put an equation. Okay, N1 over P plus N2 over I equal to N2 minus N1 over R. Okay, this R is minus big R. So we get I3. I3 is minus 2.5R. Where is it? Now, the last process is this reflecting surface. So the center will be reference point. It is minus 2 minus number. You look from this side, this is virtual side, and this is real side. So in this side, 2.5R, 1, 2, 5. So this is 2.5R. This is the final position. Finally, we introduce focus plane. Focus plane is the plane that passes focus. This is the focus, and perpendicular to the central axis of the lens. What the property it has? It features all parallel rays will focus somewhere on the focus plane after they pass the lenses. For example, these parallel lines, they will meet at the central point. If they are this one, so they will meet together at some point. Which point? Now we look at this one. A line which passes through the center of lens never changes. So definitely all these will meet this one. There are two focus planes. You have one, you have another one, okay, for one lens. Another feature, 2. All rays from source on the focus plane, the sources on the focus plane, will be parallel rays after they pass the lens. For example, the source location of focus and after the pass, they parallel to the axis. This point, they will be parallel. Which direction? Now we know this one. If this one passed the center of this, they will never change. So these parallel will be parallel to this. The ray which passes through the center of this lens will not be deflected. This is very important. Okay.